I like that. Don't need that. Okay. There, I'll push this away. We had a very easy journal, Ashima. There it is. And then we're going to go from this very easy journal to drawing on a sheet of paper. That sheet of paper is in the week 30 folder, or you can just come in, and I've got a sheet of paper for you. You can draw it at your convenience. Jeremy, welcome aboard, buddy. Are you in pre-ready? Do you have your papers ready?
I have mine.
Sweet. Jeremy, do you have yours, dude? Jeremy, you're muted.
Oh, yes, I'm here. I want to print the notes.
All right, you go ahead, man. Go ahead. Print. You need to print both things off, but you don't need the notes today. You just need the thing called PVA graph.
Okay.
So, rock and roll.
Mr. Matthew, where is the PVA graph?
It should be in the week 30 folder, my friend. Let me see.
I didn't see it in the folder.
Let me see. Ah! Dude, I put it in there. Where are you? All right, my bad. Let me get it for you. I just did it last period. That's super weird. It's not in there. Something bad happened. Let's take a look. Oh. Yeah, you know what? It doesn't like, I did it last period, but I did it, I don't know, I'll try it again. I don't think it liked the fact that I used a PNG. I think it was unhappy. I think it wants me to use a PDF. I'll try it again, though. Yeah, I bet it didn't like that it was a PNG, but let's see. Maybe. I know, downtime. All right. It's in there again. Don't ask me why it was gone that time. Second time I did it in 20 minutes. But now you should be good. I'm okay? Don't be nervous. I'm a pro. Open this PVA graph and see if it likes it. I mean, if nothing else, you can print it off. And then holler at me and let me know that you made it. What I'm going to do is I'm going to open up my screenshot of this thing. And then we'll roll. So we'll give the boys like another second. I'll show you where my thoughts are on this. This kind of gets a little bit crazy. I'm not gonna lie, but there's just a bunch of really flaky terms that continually occur. And I think the best way to physically visualize these things is to draw them first. And maybe I should give you guys, maybe I'll give you guys a little protractor so you can draw some straight lines. So, we'll draw first, talk second. I think that might be a little bit less distracting. Did you boys find that thing? Could you print it off? Free and Jeremy? Did it work?
Yeah. I'm checking it right now, so.
Okay. I think it's going to come through as like not a JPEG. So if that's a problem, I got to do something different. And I will. do something different. All right, let's take a look at what I got going on up here. Oh, perfect right there. You see this thing going around in a circle, then going around in a circle, and going around in a circle from your point of view. All right? So, we can describe where the position of that object is in space as it moves around, around, and around, and around. This is where simple harmonic motion starts to resemble plane geometry, P-L-A-N, plane geometry. It doesn't seem like simple harmonic motion is going on my record player. But let's be clear about something. This has an equilibrium straight down the middle. It's going negative boundary, positive boundary, negative boundary, positive boundary, negative boundary, positive boundary. So now we're oscillating. Remember, an oscillation is something that goes back and forth. If I have one back and forth oscillation, that's a wave. The time to do one back and forth is called the period. So, and how many back and forths you get per second is called the frequency. This has a period, this has a frequency, therefore it has attributes of simple harmonic motion. If we consider this to be equilibrium, what would we consider the outsides? These are the amplitudes. Does this have a positive and negative amplitude? Sure it does. Sure it does. So, if we keep this idea in mind, boys, are you doing okay?
Yep.
All right, good talk. So here's what I want you guys to do right now. For our position graph, what I'm going to do is I'm going to put up two special points. I'm going to put a special point up here, and then I use the dash line. And I use the dash line. Straight down, I'm going to put up a point right here. So do that on your pictures now. And I'm going to label these something weird. I'm going to label them something weird. I'll try to move that a little higher. That's all the higher it's going to go, apparently. It's projecting okay to you, right? Boys, you can see what I'm doing?
Yeah.
All right. Sorry, I screwed mine up. And now I want you to take your rulers, I want you to take your colored pencils, and I want you to draw for me a position vector that is connected to your P prime, and down here, this is your P nu. And then I want you to draw cool. Let me get my glasses. My glasses out here. See. That's wonderful. I'm going to teach you simple harmonic motion the way I was taught in college. Not the way your math teachers teach you. I'm going to teach you the way I was taught in college by my physics professor that thought that the easiest way to do this is with pure geometry. In fact, he wouldn't even let us think about the equations until we drew this with colored pencils and rulers and protractors. And that was clear back in 1954 when I was in college. It's a long time ago. But I mean, it still applies today. Okay? You guys think I was in college in 1954. Shame on all. Okay? That's super. Although I don't know. Maybe you're thinking he looks really good for 150. I don't know. It could go both ways. Sometimes I go back and forth on the issue. You know what I mean? Like I oscillate back and forth between two thoughts. I mean, it's just a phase I go through sometimes. You know, this is what I look at. Okay, I'll stop telling jokes. Period. When it comes to simple harmonic motion. Does this look like our turntable that I drew down here? Because it is our turntable. What I'm going to tell you is that if you consider your viewpoint looking at the turntable down here, it kind of looks like our object is spinning around in a circle. Okay? Well, no, I'm sorry. When you look down here, it doesn't look like it's spinning around in a circle. It looks like something that's just doing this. The circular view comes from a bird's eye view of the turntable. It's almost like we turn this thing up and up and up, and we hiked it up. We hiked it up and up and up. Okay, and then we got completely vertical with our viewpoint right there. So, all right, Matthew, that's wonderful. I think I get what you're talking about. Woo! That thing's flying. Now you're good. So let's identify some really big important characteristics. This is the real position on the circle. Tell me how many degrees away from zero you estimate that to be. Do that for me, young Calvin. Just give me a number. He just said 45 degrees. I'm with you, sir. How many radians do you think that is, Lucia? Just pull it out of the hat for me. Guessing, because it's correct. We don't know the real number. Is it 10 radians? Is it 100? Is it 1? Is it 2? Is it 10? But she said half a radian. Sure. Half a radian or 1 radian or whatever, 3/4 of a radian, we don't know. But guess what? You guys are all telling me these things because you understand what it means to be on a circle. All right? What's weird is this looks like we're on a circle. This does not look like on a circle. But that's where we could be compared to the amplitudes of an X position graph. I think everybody right here knows that if I were to stop the droning of this thing right here, I'm going to stop it in this position right here, that matches that position right there. P prime is real. I am really stuck on a circle. That corresponds to this position that we could stick in the x-axis so we can identify something as being at P nu and not being at the positive amplitude or the negative amplitude. That would be a different position. So you guys are probably with me so far. You probably figured that out. What is another attribute we have that we can talk about on here? Attribute number 1. We are moving with constant angular velocity. My record player was moving something with constant angular velocity. Okay? Now, let's label something very important. It looks like it says X max. So, X max. X max is the radius of our circle. So, whatever color you chose, mine was blue, Lucia's is green, Cushy did the wrong color for the wrong vector. Your colored vector is the vector. You're on the dotted line. The dotted line is not the colored line. The vector is colored. The hypotenuse is colored. So you colored it. It's okay. Just color it some other color. Good. Ben's got a color down there. Good. Yes. Yours is green. And Cole's is blue. Nice job. So, let's review something. And I know I'm going super slow. It's going to pick up. But this is the only way to learn this, or your brain will never do simple harmonic motion, right? I don't care how good you are at calculus. You won't be able to do this. This is going to help you. Let me wind it back so that our brain can pick up what Mr. Matthew's talking about. When you are talking about simple harmonic motion, you have to realize we're talking about cycles per second, and we're talking about frequencies. And we can also talk about where we are on the circle. Where we are on the circle is a physical location. When you look at the circle, it is a practical location when you flip it down here so you can analyze how close to the amplitude you are compared to where the equilibrium is. And we know that the equilibrium would be right down the center. I didn't even mark it on here because I think it's an assumed thing. But it doesn't have to be an assumed thing. And now we're going to say that the position I am away from equilibrium is a real vector that I could say is 10 meters away, 5 meters away. From here, or I could reference it as where am I literally around the circle? Calvin said 45 degrees or whatever, which you said about a radian, and they're both correct because there's two ways we can describe where we are around the circle. Really only one good way to describe the position vector, that's to figure it out in meters. All right, so I hope everybody is happy with step 1 and step 2. Because I'm going to throw in a time constant now. At any time t, the position will be, I'll give you a second, at any time period t. So now we're going to do a function conjunction junction. What are all these terms? That 5 right there is an angular position at t equal to 0. That omega is now something called angular frequency. What? That's angular velocity, bro. Kind of. It's something more special than that. Okay? Angular velocity is a measure of something divided by time. Oh. Angular frequency, I'll give you a second. So what makes angular frequency special is it's always radians per second for simple harmonic motion. Mr. Matthew, what do you mean that angular velocity can be something divided by time? It can actually be degrees divided by time. It can be revolutions divided by time. Has anybody ever heard the term RPM? That's an angular velocity. Okay? If you're talking about degrees per second, that's an angular velocity. If you're talking about 2 pi divided by t, that is a statement about the angular frequency. Hey, that can also be the velocity. That's true. Angular frequency can sometimes be the exact same number as angular velocity, but it doesn't have to be. It's also, our mind should catch on to that, because is it possible in a linear sense to have a displacement and a distance that are identical? Yes, but does displacement always equal distance in every situation? No. That's what we're looking at here. I'm not going to confuse you on this matter. I'm not going to go one step further, because it will become more confusing. I just need you to know that when you see the word angular frequency in your mind, you think that's a special type of angular velocity. Yes? It is, sir. Oh, sorry. I'm crushed for space up there. Yeah, there we go. All right. So everybody is happy. I am running out of space. Your paper is so vertically oriented, you cannot run out of space in the vertical sense. So I'm going to come up and I'm going to do my number 4 term just up here for the sake of doing it. And now what I am going to do is I am going to set up a simple x position here as a function of time. Does that look like x of t? Let's kind of. So I'll try and get it up in there a little bit nicer. This is an x as a function of t. So guess what I've done now? I've made a triangle of sorts. I've made a triangle of sorts. I've identified a hypotenuse, And now I found the position my P nu is from equilibrium. That line I just did there, bro, you would just measure that. You would just put a ruler right there and measure that. That's your new position. Okay, that's your new position. That's x as a function of t. But you want to know something? Let's be geometrically sound, people. Your x as a function of t is not the same number as the real position from the equilibrium of the circle. That is why we have a triangle, ladies and gentlemen. Well then, why don't you just throw a theta up there, bro? I will throw a theta up there. But here's what's strange about a triangle. Your speed around this circle dictates how many radians per second that you pick up. Your speed dictates the radians that we're going to pick up. So, if that's true, and we're talking about where you are being a function of time, where you are will also be a function of how you're spinning around this crazy circle, right? So what we have to do now is understand that we are going to substitute theta. Your position is going to depend on your frequency per time plus where you started out, your angular position at time 0. Let's see what that looks like with units. So that makes sense. My position is going to be radians per second plus radians. That's like saying my position in x equals, oh, bro, I get it. My total meters equals meters plus meters. Where I am is going to be, well, where did I start? And then how fast was I going around the circle? Okay, so that's not crazy. I'm not entirely clear why omega t plus phi equals phase, but that's what they're referring to when they're talking about the phase of something shifting around a circle. Cool? All right, now I'm ready. Now I'm ready to drop it. Now I'm ready to drop it. The big stuff right here. That right there is omega t plus phi. Not theta, this is a theta, this is a phi. Just saying, it looks like a theta, but it's not. That is not omega time period plus theta. I had to write it small. That's omega time period plus phi. We go back to here, omega time period plus phi. Woo! Now that you're killing my brain, bro. All right. Woo! Getting heavy in here. Heavy lifting. You guys all good so far? So where is the x to time of P nu is, there's an AP Physics C question. And we are going to use pure geometry of our triangle. The cosine of this triangle is the adjacent wall we built, which is our position function, is a function of time, over the hypotenuse, x max. So let's cross multiply this and substitute. Oh. Sorry. Woo! Oh my goodness. Mr. Matthew, thank you. Thank you for sitting me down and showing me one of the most complex things Isaac Newton figured out. Because Isaac Newton was so good at time functions, created calculus to describe time functions, to derive and anti-derive, then Isaac Newton sat down with a lazy Susan and a candle and an object and plotted a unit circle, devised a way you could think about circles in real terms. If you want to know where you are in reality right here, you can figure it out based on how fast it's spinning here. And all you got to do is build a right triangle. You just found the Holy Grail, children. You just found it. You just found it. Your position P nu equals the radius times the cosine, how fast you're going per time period and where you started out. That's it. That's it. Your P nu boy, you ever see it written P nu equals R cosine phase? Good luck figuring out how that transposes back to a circle. But that's how it transposes back to a circle. All right, babies? So, are you ready to do calculus without knowing calculus? Because here's what we need to do now. We need to take all these things, and I'm not saying we're going to forget it. I'm not saying we're going to forget it. I need to, I shouldn't have erased it. I shouldn't have erased. Wasted, erased it. I should have left my picture here. Could you guys be so kind as to draw me another picture here? An identical picture here with identical position mappings. P nu, there's my P. I got crazy, my bad. Positive A, negative A. And that's my position vector right there. I just also called my position vector x max. We called this x as a function of t, right? And then we called this little thing right here omega t plus phi. So now we will understand that I want you to redraw your circle like this. Change the color. And we're going to do this. V linear. So let's write down less things about this. But let's be clear about this. This thing feels like it's going to get shot off linearly at any moment. If there wasn't friction, it would get shot off linearly at every moment. Okay? So the first thing I want to write down is that particle 1 has a linear velocity that equals, oh my gosh, have we ever seen that the linear velocity equals angular velocity times r? Isn't that one of our connector equations? It is, babies. So that isn't new. That VT is negative. Because let's face it, if we were talking about simple harmonic motion of a box on a spring, that's a negative F, that's a negative V going that way, okay? And that's negative acceleration going that way too. So we're going to have to call that negative V based on the fact that our particle kind of started here and went that way. So now what? So now, let's talk about a little bit different way of drawing the triangle. You guys ready to draw this triangle a little different? Look at that now. Our sine theta of this is opposite over hypotenuse, and that v linear we said equals w x max. So we're just substituting it back in. So what does that mean for us? That means vt, and I know you're going vertical. That's fine. And we'll just put our negative in here so we're keeping track of it. And remember, the phase means the same thing as a final position. Man, are we crushing it today. That's how you kind of think of these things. Woo, babies! Woo, babies! Woo, babies! Man, that's a lot. We're done. You can put all your stuff over there on the table on the way out. I'll wash up your desks. You guys are awesome. Man, that's a lot. I know. That is an awful lot, but sometimes you just gotta grind it out. Grind it out, we did. Hey, everybody at home. Thanks for participating. I know that was a lot of information, and we're still going to have to process it eventually, but it's all good. You guys can get out of here. Thanks a million. All right. Woo! If it doesn't make sense yet, that's cool. Because that is complicated, right? How's everybody doing here today? Doing tired? Yeah.
Hi, Mr. Matthew.
Hey, kiddo.
Okay,
Just give me a second. Just give me a second. Hey, you guys have a great one. Thanks for everything. Be good.